those differ by a zero divisor, right? So over an algebra, that's kind of like a repeated root. It's not exactly a repeated root, but it's kind of like a repeated root. And that's why the solution is close to the repeated root solution, but not quite there. See it? Like, the repeated root solution would just be this and that, but not this. See, this is the novelty. This is what's born of the zero divisor. Look at that zero divisor. It's sitting right there staring at you. Where the zero divisors are is where the novelty is. So I was very, very happy when it dawned on me, oh, I need to integrate term by term over there, and this all worked out. Because this is definitely something new. I've never seen such a thing. Studying differential equations over the reals or the complexes. I mean, you never find such a weird. I mean, it's all because linear independence of functions over an algebra. It's quite a bit more nuanced than what we study in 334. I mean, do we study linear independence in 334? Debatable. You think this is weird. Let me show you a little bit about degenerate ODEs. So non-degenerate, what that means is the leading coefficient is a unit. If the leading coefficient of the nth order ODE is a unit, it's non-degenerate. If the leading coefficient of the ODE is a zero divisor, all bets are off. I think that was the definition. I should actually check. I have a whole section on these things. I did write it. Promise. Let's see here. Yeah, so Nathan and I said that if alpha is in the zero divisors of A, then a degenerate nth order ODE has the form alpha d to the n plus some polynomial in the differentiation operator acting on eta equals to 0. So this is a degenerate nth order AODE. Alpha is a zero divisor. So my theorem for the existence and uniqueness of fundamental solution sets for non-degenerate ODEs gives me joy. Working out the details of it for specific algebras and specific differential equations can be quite disturbing at certain steps in the journey as you're learning to grapple with these new ideas of linear independence over an algebra. Really module theory. But all of those exciting familiar features in the existence and uniqueness theorem, they're gone for degenerate ODEs. It fails in both regards. It fails in the sense of uniqueness, and there's other ones that fail in the sense of existence, in the sense of solving initial value problems. You can state initial value problems for degenerate ODEs which simply cannot be solved. And there can be an infinite solution set. For example, a stupid example. You don't have to work hard at it. Just take your favorite zero divisor, 1 plus j, right? 1 plus j times, I don't know, how about dw dz? We can still get lots of mileage out of the hyperbolic numbers. It's one of my resolutions to work more with other algebras. I feel like it's a little bit too hyperbolic all the time. It's really not all I'm interested in. It's just my lazy two-dimensional go-to. Most of the weirdities are already there. It's like working with 2x2 matrices in linear algebra, right? They have almost all of their exciting features already, but not everything. So can you guys tell me W equals what will solve this? I'll let you fill in the blank. What I'm put over here is g of z, where this is any g in the hyperbolic differentiable functions. any hyperbolic differentiable function. What do you fill in the blanks for me? Well, zero, yes, zero does work, but how about something more exciting? 1 minus j, right? Yeah, so that solves it for any choice of g. First order differential equation, infinite solution set in the sense of hyperbolic linearity. It's not nice. That the other thing that can happen, and Nathan has a really nice theorem in here that describes these in some rather systematic way. His theorem 6.3, consider constant coefficient AODE L of y equal to L of w equal to 0. This AODE has solutions of the form c times f of z, where c is a fixed constant in A, and f of z is an arbitrary function in c of A, if and only if L is an element of the zero divisors of the ring of differential operators. So Nathan's theorem basically says this happens, this is a constant times g of z, right? So his theorem essentially says this theorem. If solution set has form like that, c g of z for all g in CA, then in the solution set of what? Of like L of W equal to 0, okay? Then he says that L is actually an element of the zero divisors of the ring, polynomial ring of the differentiation operator over the algebra. So this is the ring of polynomials and the differentiation operator, zero divisors of that ring. Now there's further theorem that says, there's something called McCoy's theorem, which basically says that you can describe the zero divisors in this ring. A zero divisor in this ring has the form, it doesn't have to be that you can factor out a zero divisor. So if something is in here, what this means is that there exists a beta such that beta times L is equal to 0. So certainly if this L is 1 plus j times, d dz, so the beta that you multiply this by is just 1 minus j. And certainly it's true that some of the zero divisors in the polynomial ring would be, you take an operator, if you can factor out a common zero divisor from all the terms, then it would be one of these zero divisor operators. But there's other cases, like you can have one that you can't factor a zero divisor out, and yet there's something you can multiply by it to get 0, like that. There's an example. I have an example in here. This one. If we look at E2 d squared, E1d plus E1 plus E2, this thing, what algebra is this on? The direct product algebras? It's still the hyperbolics, in different notation. So the direct product of R and R, this guy. So the zero divisors, what are the zero divisors in here? E1, E2, right? E1 and E2 are the zero divisors of the direct product algebra. So this is degenerate, right? Because it's E2 times d squared, and this is like my quote-unquote Q of d, right? Let's see here. Trying to think. Oh, this is not the example I'm looking for. This is just the one that illustrates the other phenomena. I'm sorry. Which I said was you can't solve every initial condition. So how would you solve this? I mean, we can solve this. It'll take us all of 3 seconds. I'm not joking. I mean, this eta, we could write as, say, y1, y2. Yeah? And so, let's see here. How's that go? Right. Exactly. So we end up with, how's it go? Say that again? Yeah, I think we end up with y1 prime plus y1, comma, from this one, y2 prime prime, plus y2. When you sort through it, what it means. So this gives us, of course, y1 is like c1 e to the minus, yeah, I need to be careful here. Yeah, they have, these are different derivatives. I'm sorry, I should be more careful. This is partial x. These guys, oh, unfortunate, partial y. Ah! All right, let me fix that. Let me fix it. So let's suppose that that is f comma g, all right? F is f of x. G is g of y by R2 differentiability. So this really sorts out to partial x f plus f and partial squared y g plus g. All right, equal to 0, 0. So this has solution f is c1 e to the minus x, and g is what? c2 cosine y plus c3 sine y. And that's a, yeah, okay. And so what I say is if you look, suppose you want the initial condition eta 0, 0 to be 0, 0. And eta, oh, typo. That's supposed to be eta prime of 0, 0 to be 1, 1. I got an F right there right now. That's wrong. Oops. I got to fix that. It's impossible to fit this set of initial data for this second order differential equation. You can't have that being both 0 and 1, which is what you'd need. So this is an example of a degenerate ODE which does not permit a solution to an initial value problem. So those are the two phenomena that happen for degenerate ODEs, and that's why they're degenerate. Anyway, so we're done for today. Thanks, guys.